Hi there, this is exercise 22E. This is actually a very final video I'm doing for the A-level maths course, and it's an extra one that's not in the textbook, but basically we as a maths department noticed that this type of question keeps on coming up. And it's basically questions with hinges, which rely on you using our knowledge of forces and moments and everything else. But the hinges on this picture, for instance, is denoted by this A here, and this A tells me that I've got to just be aware that it can move. And of course it will move because it's got a force coming down through here. The weight of this beam. And effectively the only reason it doesn't move is because we've got presumably a tension coming up through this support wire here. So we end up with two forces acting. And actually at these points there might be forces as well. So we've got to be a bit careful. Let's have a go at some questions anyway. So this is a starter question. It's not just part of an exam question. Very similar to what we've just been doing, actually. If you look at it, it says got a non-uniform beam. And of course, non-uniform beam basically means the weight doesn't act at the centre. But very kindly, they've told us where it acts. You can see it is acting at 85 newtons, 3 meters along. Then 2 meters further, you've got the end of this beam. And what we've got? We've got all forces acting in the same vertical plane. It means you just look at the picture and it works. Calculate the reactions of the supports and the beams. All right, so now I know what I'm doing. There's a reaction here, which I'll call RA, normal contact force if you prefer, and this is RB. And I suppose we've got these two approaches. We can use forces up equals forces down. When I do that, I just get this very straightforward RA plus RB is equal to they are going up, so 85 coming down. So that's my very first thing. And a lot of people miss that one out. That's probably the easiest one to do. It saves you having to do moments twice, essentially. And then I might as well take moments. I'm going to take moments from A. So on this far left-hand side, I'm going to take moments. And I've got two forces acting. I'm allowed to discount the forces acting at A because there's no distance. And if you remember, moments are force times perpendicular distance. So that 85, that 3, they are going this way round. If I was to rotate, that would be a clockwise moment, whereas this one would be an anti-clockwise one. So we can quite happily say that 3 times the 85 is equal to, what's that? The distance, total distance now, be careful, not 2, it's 5 times by the RB, whatever that reaction force is. Now 3 times 85 sounds like 255 to me. I was just going to get my calculator out and I was saved. Equals 5 times the RB. Presumably then, RB is the 255 divided by 5, which is 51 newtons. So I now know what RB is, that's 51, and of course, I suppose straight away I can work out the other one. RA must be the 85 take away the 51, given that first formula I wrote down, so that's 34 newtons. And there I think I have my answers for those two things. So 34 and 51. So look, I've got them right. That, of course, has no hinges at all. And this question, or series of questions, is meant to be testing us on hinges. So let's have a look at a question with a hinge. And it's actually the same picture we started with in the on the front slide of this. So what have we got? We've got a beam coming across here. And that says it's got a uniform rod of weight 20. It's good that it's uniform because that means I know it's acting there. Got a 20 Newton force, but you always be careful. It's not a Newton force. If it's a mass, you should think of it in terms of like times it by 9.8 or G. What we've got, that's 1.5 meters across, and then we got the full 3 meters. All right, and this is, I did say there's probably a tension. I think there's got to be a tension pulling up. That's what that does. It stops it rotating and pulling down. Okay, so what we've got, the end A is freely hinged to a point on the vertical wall. Horizontally, it's held horizontally and in equilibrium by a light inextensible string. The one thing I would say is it's very dangerous on these kind of questions to do forces up equals forces down. And that's simply because I have no idea what forces are acting here at A. Or at C, for instance, there must be forces acting there. And some of those forces might be up and down. So I think it'd be very dangerous doing forces up equals forces down here. So I'm not going to do that. Instead, I'm going to take moments, and I'm going to take moments at A. Why not? A seems an obvious place to do it. Now, the advantage of taking moments at A is it basically rules out both those two sets of forces, which are kind of in line with it. So that's a real reason. B wouldn't be anywhere near as useful because I'd have to consider the forces acting at A. But if I take at A, it wipes out a lot of forces. So what have I got? Now this 3-meter length is split in two, and I've got this 20 Newton force coming down. I think that would make it go clockwise. And this T effectively is kind of like pushing up if I resolve it. And that would make it go that way. So I think this is an anti-clockwise. It would pull it round that way, yeah. So what have I got? I've got the distance 1.5 times by the 20 Newton force, and that's got to be equal to the distance of 3 times by t. I've got to resolve it, remember. I need an angle. I'm going to say t sine theta, where that is theta. So I've got to do a bit of sums over here. So, well, I know that tan theta, just looking at this picture, is 1 over 3. That will give me my theta. Presumably I can then just sign it. I could do it exactly, but I don't really think I need to worry too much about this. So let's just get my calculator in some kind of shape. The inverse tan of 1 divided by 3, make sure you're in degrees, is 18.43 degrees. And on that basis, I should be able to work out sine theta, the sine of that answer. Well, typically, I just did the wrong button. Sine of that answer is 0.316. So I can use that, and I can use the exact number, of course. So that tells me that t equals 1.5 times the 20 divided by that 3 and divided by sine theta, which I reckon is now 0.316. So what's that? 1.5 times 20 is 30, divided by the 3, divided by the answer I just got. And I get 31.6 newtons. Where is that? There. 31.6 newtons. That's the tension in the string, which of course is what it wanted me to do all that time ago. 31.6 newtons, good. Now, a second question. A rectangular frame consists of 4 metal rods. So straight away, right, I've got 4 metal rods. Now, I'm trying to see what's going on. A and B are vertical. So A and B, and so this is sort of standing up, I suppose. That's what that tells me, because they're vertical. And each is 40 centimeters long. So it's a bit weird. I've got these hinges here. The frame is freely hinged at A. So I suppose some movement can occur at these two places. I'm not sure if I particularly understand what's going on, but I'm just going to do it anyway. It tells me masses. So I've got AD has a mass of 0.7. Where's AD? So that's got a mass coming down here at 30, I suppose. We've got a mass of 0.7, so therefore a weight of 0.7 g. And also this has got a weight coming down equally at 30. And that is, what's that say? BC has got a different mass, it's 0.5. So 0.5 g. The other ones, A, B, and CD, are both have a mass of 0.2 kilograms. So it's a bit weird, but I'm having to think of this AB as one piece of metal. And that's why I was saying about, I don't really understand what the hinges are going on about. But each of them have a mass coming down from it, and therefore a weight coming down from it, of 0.2 g. Of course, g is just 9.8, isn't it? So I'll just write that there, 0.2 g. And there's my forces acting on this picture. Now, of course, there's other forces potentially, because they've said sketch a diagram showing the directions of the horizontal forces acting on the frame at E and F. So there must be a force going through F, some direction. And I suppose my question is, which direction is it going in? And And let's do this. I'm going to think about F, and I think the best way to do this is to think of taking moments at F. I'm not going to take moments at F. I'm going to think about it. And if I take moments at F, I reckon this is going down. I've kind of got from F, I've kind of got a distance coming here. Then I've got a force here and also a force here. But you'll notice between them, they have a kind of a joint force going across. And then I've got another one even further away, and this 0.2. So I'm kind of thinking these two acting together. And then I've got the one over here acting. Now, I don't care about this 0.0, this one, because effectively that's going straight through F. So they're the only forces I have. Now, all those forces are basically pulling round in, I suppose, the best way to describe it is a clockwise direction. And I think that tells me something about E, actually. There must be a force. If this thing isn't just to fall apart, so I'm assuming this is all in equilibrium. Otherwise, the whole thing would move. If this thing is to stop itself from moving, there must be a force pushing back, because then I would have a moment on F from E. And yeah, I think that would then be an anti-clockwise force. So I think the force at E must be pushing to the right. And since this whole system doesn't fall apart, I think there must be a force acting on F pointing to the left. Now that's a bit weird. So I might have to go through that with you in class. Now, part 2 says calculate the magnitude of the horizontal component of the force acting on E. Okay, so I suppose really acting on E, I need to find this force here. All right, so I think I'm going to do what I just set out. So I've got this distance here is 0.3 meters, and this is another 0.3. And you can see there, and I suppose I need to do this. Okay, so I've got 0.3 is my distance, but I've got two forces acting, pulling straight down through that line. And they add up to 1.2 G, so 1.2 times 9.8. Plus, I've got another force, which is 0.6 away. And that's coming down there, you see, and that's 0.2 G. So times by 0.2 times 9.8. And I'm going to draw the force acting at E as this, I'm going to call it F. F is a bad thing to call it. I've got an F up there. Let's call it X. So that is equal to the distance there, which is 0.2 times by the force. So I haven't got this hasn't got a G in it, so it's just X. So what do I get when I do that? I'm just going to type that in. Get 0.3 times 1.2 times 9.8 plus the 0.6 times by 0.2 times 9.8. Okay. And I think I just divide that by 0.2. 3.52. Or 23.52, sorry, I couldn't see it on the screen properly. So when I've done this, then I've got 4.704 equals 0.2x, and therefore x, according to me, is 23.5. I suppose to 3 sig figs, 23.5 newtons. And have I got any answers for this? Oh, I have yeah, look, I have. And my answers are saying left and right in the right directions, right at E and left at F. Good. So that is right. Now that's a very, very brief introduction into this topic. I've got a third example, and then I was expecting not to get onto this one. So I've actually got 2 class examples for you when we do this in class. So here's a third example for us, and hopefully this will be the last one that we need to do. And then we can wrap this all this A-level math stuff up. So we've got a uniform beam AB, and again, I like the fact it says a uniform. Just get my pen, it seems to have gone off. A uniform AB there. So that tells can act at the centre of weight 70 newtons. Again, notice always check whether it's a mass or it's a proper weight. So that's at 1.4 meters along. The beam is freely hinged at A. So there's my hinge. So there's the ability for it to move down, you see. I suppose that's the thing that's key. The fact that it's moving down or could move down means there must be a force acting up here, which I'll call it tension. Have they called it a tension? They've called it as a force. Or okay, I'll change it to an F. So we've got a force acting upwards in that beam. Oh, they've given us the dimensions of this little triangle as well. 0.5, 1. Now, those of you who know your Pythagorean triples, that sounds like 1.2 there. Now, you could prove that using Pythagoras. You could do 1.3 squared minus 0.5 squared. This is 1.2 meters. And of course, that then, I'm going to probably end up needing that angle there, which I'm going to call theta. That then will give me the theta. In fact, I can just write it now. It will tell me I'm probably going to need sine theta, so I'm just going to write sine theta. It's going to be opposite 1.2 over the hypotenuse, which is 1.3. And I'll just keep that in the back of my mind. I'll probably need that in a bit. So what do we got? Calculate the force exerted by the strut on the beam. And again, because I've got these potential forces going on at A and D, I'm not going to do up equals down. I'm just going to take moments, and I'm going to take moments at A. So I'm going to take moments at A. What's it say? Okay, so what we got, so from A, I think that force there is the one that's going to be pushing anti-clockwise, whereas the other two, I think, are both clockwise forces. So what have I got? I've got 0.5 distance times by the force, which is F, but it's F sine theta. And I know what sine theta is, I've worked it out. So that was wise to do that. And that's got to be equal to the other two forces, which are much, much easier to do. It's 1.4 times by the 70 plus 2.8 times by, what is it, it's 50. So if I just do that now, 1.4 times 70. 1.4 times 70 plus the 2.8 times 50. That gives me 238. So I've got 238 newtons according to me. And then in addition to that, I've got on this the left-hand side, I've got 0.5. I now know that sine theta is 1.2 over 1.3. Now I could work it out. I could, for instance, now inverse sine it and then kind of put it back in, but it's almost pointless. I just know it's going to equal that. So therefore, I can rearrange that. F is the 238, and all this moves over. So I'm going to divide by 0.5, divide by the 1.2, and times by the 1.3. That gives me 515. 516, I suppose. Yeah, I'm going to say 516 newtons. And there's my force. The magnitude of the force acting on the beam. Calculate the magnitude of the forces acting at A. Oh, look. See, this is what I was talking about. And I'm pleased this has come up because we need to realize that we have no real idea what forces are acting at A or D. Now, one way of doing it then is to say to ourselves, well, hang on a bit. We can just pretend we know almost. I'm going to draw it. I'll draw it here. There could be a force coming straight down, you see. I'm going to call that, I'm going to call it F. Don't like the fact that I would use F, but they'll do F in the Y direction and going sideways. And I'm not sure which way they'll go. I'm going to say Fx. So I'm going to think of these two forces. And let me first of all, I'm going to think to myself, I'm going to go in the up and down direction. And if I go in the up and down direction, what have I got? Well, I've got, I suppose, Fy goes down, based on my picture, anyway, plus a 70 goes down, plus a 50 goes down. And now, because I'm considering all the forces, I think I'm safe to do this. I can say, well, all of those act on the beam must equal all the forces acting on the beam going up. And the only force going up is this F force. Oh, well, I've got to be slightly careful. It's at an angle. I've got to resolve it in that direction. So it's F, which I found was 516. What was it exactly? 515.666.67, I'm going to say, times, now to resolve it in that way, I've got to times by the sine theta again. sine theta, which of course I know is 1.2 over 1.3. So what does that give me? That gives me Fy plus 120 equals, let me just do that, 515, yeah, it's still on my screen, times by 1.2 divided by the 1.3. And again, some of you will be working out theta instead. What do I get? I get 476 for that. And so presumably Fy, when I move the 120 over, is 356 newtons. I've now got my Fy force. Now, how do I get my Fx force? Well, Fx, what forces are going left and right? Just looking at this picture, there's only two forces acting on this beam going left and right. So I've got Fx pushing right. Oh, actually, that's pushing right. So presumably my Fx is going that way. I've just realized my Fx is actually going that direction. So now my Fx, and that, if you're not sure about that, that's because that's got to counterbalance this pushing right force here. And what force would that be? I think that would be Fx is equal to my F force times by cos theta. And again, if I look over here, I didn't think I'd need my cos theta, but I'm going to do it now. Cos theta is adjacent over hypotenuse. That's 0.5 over the hypotenuse, 1.3. So this is F times, that's a bit dodgy, so that's all right, dot 5, what was it, 515.67 was my F force, times by my 0.5 over 1.3. What does that give me? 515.67 times 0.5 divided by 1.3 equals 198. 0.3-ish, I suppose. Just doing a bit of accuracy there. And the reason why I want that bit of accuracy, because it actually says find the magnitude of the force. Now I've got the components in Fx and Fy. So I suppose to get the magnitude, usually written like that, with like vectors with lines around it, you have to do the square root of these two things. It's Pythagoras effectively. I mean, broadly speaking, I've got the force going left of, 198 newtons. And I've got a force going kind of down after that of 356 newtons. And so you can always find, when you do this, the magnitude of that vector. And if I wanted the direction of it, I could find the angle as well. But I don't, no, they haven't asked for that. So magnitude of F is 356 squared plus 198.3 squared, all square rooted. What's that give me when I do it? So I can square that answer with my calculator, plus 356 squared, square root of the answer, 407.5. newtons. And so what do the answers say? What have I got? 407, 408. Yeah, look, 407.5. They were willing to accept, interestingly, either of those two answers. From 516, we got 516 as well, so that worked. Now look, I've got a class example for you. We'll worry about that in class. You can see it's very similar actually to what I've just done. And then I've also got some exercises on a worksheet for us to do, because I say this isn't in the textbook, but we've started doing it because it's started to come up more and more often. So look, thank you very much, and I hope that was useful, and we'll go through these in class. Thank you very much.